Okay, so welcome to the final session of Study Ready. The topic of today is trigonometry. So what we're going to see is we're going to be working with right-angled triangles, and we're going to see how to apply this theorem called the Pythagorean Theorem, how to use these functions called sine, cosine, and tangent to help us relate the angles of right-angled triangles to their sides. Okay, and right-angled triangles in this Pythagorean theorem will crop up all over the place, even if you're not studying maths. It will, if you're doing, any quantitative subject, you will find this Pythagorean theorem cropping up. So I'm just going to share my screen. So before we get on to working with right-angled triangles, we need to give some names to the different parts of the triangle. Okay, so first of all, what is a right-angled triangle? A right-angled triangle is any triangle that contains an angle of 90 degrees. Okay, and an angle of 90 degrees is usually depicted in a diagram like this, using these two lines which are perpendicular to each other. Okay, so these two lines will usually denote a 90-degree angle, and this 90 will usually be omitted from a diagram. So when you see these two perpendicular lines, you should just know, okay, this is a 90-degree angle. I have a right-angled triangle. We also, if we're interested in one of the other angles of the triangle, not the 90-degree one, and the degree of that angle is unknown, it's very common to call that angle theta. Okay. So for some general unknown angle, we might call it theta, and this angle is usually denoted with like a curved line, okay, compared to these two perpendicular straight ones. So now we've kind of named the angles inside a triangle. We can also name the sides of a triangle, but you have to be very careful here because when we name the sides of a triangle, as we're going to do, we actually name them relative to an angle that we're interested in, okay? So for instance, if we're interested in this, we have a 90-degree triangle, as shown here, and we're interested in some angle theta. Now we're going to name the sides of this triangle relative to theta. And what do I mean by that? I mean, if you look at this opposite side here, then we name the side opposite if it's opposite to the angle that we're interested in, theta. So if you look at theta and you look opposite to theta, then this side is called the opposite side. Similarly, we name the side which is next to both the angle theta and next to the 90-degree angle as the side called the adjacent side. So the side named adjacent is the side which is next to both theta and the 90-degree angle. So notice the side named opposite and the side named adjacent very much depend on the angle that we're interested in the triangle. So for instance, if we're interested in this angle up here, then this side would now be the adjacent side, and this side down here would now be opposite because it's opposite the angle of interest. And the last side that we name in the triangle is called the hypotenuse, and this is the side which is opposite to the right angle of the triangle. So we look at this right angle, we look opposite it, and we find the side which is always called the hypotenuse. Okay, and you can see that's not going to change depending on whether you're at what angle is theta here. The hypotenuse is not going to change. Okay, it's always going to be the one opposite the right angle of the triangle. So let's just cement that understanding by taking another right angle triangle, which I've drawn here, and seeing if we can label the sides relative to theta. So let's ask ourselves, what is the opposite side? Well, the opposite side, you look at your right angle triangle, you notice you have your angle theta, you look opposite to that, and therefore this one you label as the opposite side. Then where's the adjacent? Well, what side is next to both the angle theta and the right angle of the triangle? Well, it's this one here. This is the adjacent. And last but not least, you have the hypotenuse side, which is always opposite the right angle. Okay, so we look at the right angle, we go opposite, and we write hypotenuse. So it's really important that, you know, if we have any right angle triangle and we have an angle of interest, you can quickly name the opposite side, the adjacent side, and the hypotenuse, because you'll need to do this, and you'll need to just be able to, you know, do it super quick without having to think about it. So practice a few of these. Lastly, I just want to say, sometimes people label the vertices of their triangle. So they'll have a triangle like this, and they'll label these vertices here, here, and here as P, R, and Q. Okay, notice I'm not saying the angle is called P. Okay, I'm just saying the vertices, so this point, and this point. Okay, and if they label these vertices P, Q, and R, then sometimes they'll actually refer to the triangle, like they'll give it a name, and they'll call the triangle PQR, and they might call this side might be called PR, the side PR. This side might be called the side PQ, and they could call this side the side QR. Okay, so these names don't refer to any angle theta, they just refer to the names of the vertices which someone gave in advance. And they have nothing to do with the interior angles. Yeah, just look out for this because you will see it come up. Okay, so the first, and now that we kind of know how to name the different parts of our triangle, we can look at the two massively used results, which are very, very helpful and handy to know. The first one is the Pythagorean theorem. And the Pythagorean theorem is actually a geometric result. So if you want to look up the proof for the Pythagorean theorem, you'll see it as a very geometric argument as to why this holds, which we're not going to go through today, but you can look this up. What the theorem says is, it says if you look at the hypotenuse of your triangle, which is the Z, so you look at Z, and you square it, then this is actually equal to the sum of the squares of the other sides. Okay, so it's equal to the sum of this side squared plus this side squared. Okay, so your hypotenuse squared is equal to the sum of the squares of the other sides. So that's the first result. There's a second result, which is very general, and this Pythagorean theorem only applies to right angle triangles. Okay, this second result applies to any triangle, and this result is about the interior angles of the triangle, and it says that for any triangle, not just a right angle triangle, the sum of the interior angles, so the sum of theta 1, theta 2, and theta 3 is 180 degrees. Okay, so we have these two results. Let's see if we can use them. So, example 2, part I. This asks to find the hypotenuse length Z in meters. Okay, so how are we going to do that? Well, let's use the Pythagorean theorem. That says that Z, so this is the answer. This is going to be our answer. This said that the Pythagorean theorem says that Z squared is equal to the sum of the squares of the other side. So that's the sum of 30 squared and 20 squared. Okay, to solve this equation, I take a square root on both sides of the equation, and I only take the positive square root because we're talking about a length, and lengths are always positive, so I'm taking a positive square root, 30 squared plus 20 squared. And if I put that into a calculator, which I have done here already, as you can see, you get 36.056, because I'll just round up. So you get 30, what did I say? I said 36.056. And this is in centimeters. So to turn it to meters, I can say Z is equal, to go from centimeters to meters, you divide by 100. You get 0.36056 meters. That's your final answer. Now, part II of this question gives you a new triangle, and it just says to write x in terms of these variables y and z. So these x, y, and z are kind of, they're just names. They're just names of variables. And it wants you to write x in terms of whatever y is and whatever z is. Okay. So let's write down the Pythagorean theorem again. This is our answer. It says z squared is equal to the sum of the squares of the other sides, which is x squared plus y squared. Okay, but we want x in terms of y and z, so let's rearrange this by writing x squared is equal to z squared minus y squared. So I've just minus y from both sides of the y squared from both sides of the equation. And now again, I'm going to take a positive square root of both sides to get x is equal to z squared minus y squared, all square rooted. Okay. So let's do another example using the second fact that we learned, that was the sum of the interior angles is 180. So for example 3 part I, let's find what theta is. Remember, we said the sum of the interior angles of a triangle is always 180. In other words, 180 is equal to 40 plus 40 plus theta. Right, because these are this is on this right hand side is the sum of the interior angles of this triangle. Has to be 180. So if you take 80 away from both sides of this equation, you get theta is 100. And then for this part II of this question, we're given a right angle triangle, and we're told to find theta. So again, we know the interior angles is equal to 180. So 180 is equal to the interior angles, which is theta plus 30 plus 90, because remember, these perpendicular lines mean you have a 90 degree. So if we take away 120 from this side of the equation and this side of the equation, we're left with theta is equal to 60. And that would be the final answer. Okay, so in this page, we really just looked at two fundamental facts about triangles. The first is any triangle, the sum of the interior angles is 180. And this first fact we looked at is the Pythagorean theorem that says if you have a right angle triangle, okay, you have to have a right angle triangle, but if you do, the hypotenuse squared is equal to the sum of the squares of other sides. So the last bit of this study ready session is now we're going to be relating angles to the sides of triangles using these functions sine, cosine, and tangent. Okay, so mathematically, instead of writing out sine, cosine, tangent all the time, mathematicians abbreviate the names of these functions, and these functions are now are commonly just referred to, and in your calculators, it's how you'll see they're referred to just as sine, cos, and tan. Okay, and what these functions do, these are just functions, they're regular functions. They take in a number, they spit out a number. Okay, they're just like, how you write f of x, or you write, y of x. Y and f here are just functions that take in something x and spit out another number. So it's the same in this case, sine is just a function Takes in a number, it spits out a number. Cos is a function, it takes in a number, it spits out a number. Same with tan. But these functions are very useful, and you'll see why. What they can be used to do is either they can be used to find an unknown angle given two sides of a triangle, or they can be used to find an unknown side of a triangle given one side and one angle of that triangle. And how can they be used? That, well, we have these three formulas here. Okay, the first formula says you take this right angle triangle, you have some angle theta that you're interested in, you label sides. The opposite side you label x, the adjacent side you label y, the hypotenuse you label z. This first formula says that sine, this function sine, if it takes in theta as an argument, okay, of course you could write that just to reiterate the signs of function, taking in theta as an argument. Then whatever theta is, this will always be equal to the opposite side of your triangle, whatever that is, divided by the hypotenuse of your triangle, whatever that is. So sine of theta is the ratio of your opposite side to your hypotenuse. Whatever these theta, x, y, and z are, they have to obey this relationship. And you have similar results for cosine and tangent. For cos, you have cos of this theta is equal to the ratio of your adjacent side and your hypotenuse side. And whatever this function tan is, and whatever theta and y are, tan is a function that when it takes in theta, this is always going to be equal to the ratio of your opposite side x over your adjacent side y. And the way to remember that sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent is this mnemonic, which is for sine you have so, which is opposite over hypotenuse, hence the O and the H. For cos you have ka, which is adjacent over hypotenuse, hence the A and the H. And for tan you have toa, which is opposite over adjacent, hence the O and the A, right? So normally people say so ka toa to remember this. You just need to remember so ka toa. And I should point out from these three formulas here, because these are just functions, sine, cos, and tan, you can take their inverse. You know, you've probably seen you have a function f of x equals something. You can find out what x is from this if you take the inverse of f on both sides of your equation. So if you take the inverse of f on this side, you're just left with x. And on the right-hand side, whatever it is, you get the inverse of whatever I wrote here, you'd get f inverse of that. Okay, and you can do the exact same thing with sine, cos, and tan because they're just functions, which is what I've written down here. If we take the inverse of sine in the first function, in the first formula, you get theta is equal to sine inverse of x over z. The second one, you get theta is equal to cos inverse of y over z. The third one, you get theta is equal to tan inverse of x over y. So like taking the inverse here, you can actually get theta as the subject of your equation. Okay. So let's do some questions. Let's do some questions. So the first one is, I've labeled this triangle L, M, and N. What is the length? The length of the side LN. Okay, how are you going to work this out? Well, we're going to try and use our formula for sine, cos, and tangent. Okay. Now, which one do we need? Well, we know this angle is 55, and we know this length is 18. So let's label the sides, the opposite, the adjacent hypotenuse with respect to this angle? Well, we know the hypotenuse is always opposite the right angle, so this is the hypotenuse. We know that the adjacent is always next to the right angle and the angle you're interested in, so this is the adjacent. And we know the opposite is the one opposite the angle that we know, so this is the opposite. Now that we know these, we realize, we want to know the hypotenuse, okay? And moreover, we know the adjacent. So which of these formula do we use? When we know the adjacent, so we know y, but we want to find z. So which one has y and z in it? Because remember the z is the hypotenuse. Well, it's this, it's the cosine, okay? So we're going to use that. We're going to use that, the hypotenuse, but we're going to use the cos of our angle, which is, we're going to use the cos of theta is equal to the adjacent, which is y over the hypotenuse, which remember we called z. So this is the formula we're using. Here, our theta is 55. Our adjacent side is 18 centimeters. And our hypotenuse, or our side ln, which is the hypotenuse, is just, we're going to call z. Okay, so I'm actually going to call this hypotenuse z. We'll say that as length z. And so we want to find z here. Or do you know what? Let's call it. Yes, let's say it's z. So then we rearrange this, and you get z. You multiply both sides by z to rearrange. You get z is equal to, and then so you multiply by z, and then divide by cos of 55 to get. Okay, and we can plug this in on a calculator. Okay, we have 18 divided by cos of 55, which apparently is 31.4. Let's round up. You get 31.4. And this would be in centimeters. Okay, so here we used our sine, cos, and tangent. Well, we actually just use the cosine function to find a side of a triangle given an angle and another side. Now we're gonna do a similar thing in this next example. So here we're asked to find x. So again, let's do the same thing. Let's actually just put here our formula so we remember. In fact, let's put let's copy this. There we go. So now let's find out, let's label the sides of this triangle first of all. This is the angle we're interested in, so this one's the adjacent. This one's the opposite. This one's the hypotenuse. Okay. Now don't get thrown off that the hypotenuse is now called x. Remember, x, y, and z are just labels, okay? Just because now x is where the hypotenuse is, we still use, side is still the hypotenuse, okay? So we know the adjacent, we know the opposite. We know the opposite, and we want to know the hypotenuse. We don't care about the adjacent. So which of these three formulas doesn't have the adjacent in it? It's SO, okay? SO is only related to, or sine is only related to the opposite and the hypotenuse. So here you would have sine, sorry, let me write in red. Here you would have sine of your angle, 62, is equal to, let's look, sine is SO, which is opposite over hypotenuse, so which is 16 over x. We do a similar thing to the last example. We multiply through by x and we divide by sine of 62 to get x is equal to 16 over sine of 62. Okay, and I could put this in onto my calculator, so like I did in the last example, and you would get some answer, some result for x. I'm not going to do that because we don't need to put every single thing into the calculator. You guys can do that yourself. The next one, again, is a similar question. Again, another triangle, and we asked to find this length x. So let's label our sides again. This is the hypotenuse, because opposite the right angle. This is the adjacent, because next to the right angle and the angle we know. And this is the opposite, because opposite the angle that we're interested in. Okay. So we know the adjacent and we want to know the opposite. Okay, so we don't care about the hypotenuse here. So which three of these doesn't have the hypotenuse in it? It's the tangent or the TOA, which is the opposite over the adjacent. It doesn't include the hypotenuse. So let's try and use that one. That one says that tan of our angle, which is 60, is equal to the opposite over the adjacent. Here the opposite is x and the adjacent is 3. So let's solve this for x. We solve it by multiplying through by 3, and we get x is equal to 3 times tan of 60. And again, I could put this in on my calculator. One thing I should note is remember to work in, I've written everything in degrees here, but your calculators might be in radians mode, which is just another way of naming angles, really. It's just another metric for angles. Yeah, so make sure if you're working in degrees, you've got your calculator set in degrees. If you're working in radians, you've got your calculator set in radians. So I'm not gonna put this one into the calculator either, but you guys can do that yourselves. So let me just paste this again. So we have this question. So this one says, this one's a kind of diagram, and you're meant to be able to, construct a triangle out of this diagram, really. It says you have a chisel, and it wants you have this kind of diagonal kind of bladed bit, I guess, at the end of the chisel, and it wants the angle of this blades bit here to this edge. So how are we going to find this angle? Well, let's build a triangle out of this, okay, like this. Let's build a triangle, okay? And if we zoom in on that triangle, we actually forget about the whole rest of the picture of this chisel. You're actually getting a triangle. Imagine these lines are all straight. This is a triangle of some angle theta, some right angle, a length here, which is 1, because we've read that off here, and a length at the bottom, which is 1.5. And this is all in centimeters, this question. So here now, let's always name the sides of our triangle. We know this is hypotenuse. This side is the opposite, because opposite theta. This side is the adjacent. It's in between the angle theta and the right angle. And now which one of our 3 formula doesn't include the hypotenuse. Well, again, it is the ones that just include the adjacent. The opposite is TOA. It's opposite over adjacent. So we know that from this, we know that tan of theta is equal to the opposite, which is 1 over the adjacent, which is 1.5. So I'm going to write this as 1 over 3 over 2, because 3 over 2 is 1.5. And I'm going to simplify that to be 2 over 3. Okay, now I'm going to have to use what I showed you before, which is we're going to have to take the inverse. We have to take the inverse of this tangent function, okay? And if we take the inverse on both sides of this equation, you end up with theta equals tan inverse 2 over 3. Okay, and it's as simple as that, you know. You can plug this into your calculator, which we'll do. So tan, oh, let's clear all. We'll say tan inverse of 2 divided by 3 is apparently equal to 33.69. So this is 33.69. And I didn't round up there. Yeah, so this is everything really. This is all you need to know. So I've left 2 examples. The next one is slightly more difficult. Okay, the next one's slightly more difficult, and then the last one is also, I would say, slightly more difficult, because you're actually now kind of finding theta in terms of this angle x, in terms of this length x, and so x is going to be left in your answer. So this is what's difficult. In example 8, x is going to be left in your answer because you're finding theta in terms of it. So you might find that a bit tricky. And then example 7 is slightly more difficult because it's similar to this, very, very, very similar to this chisel question. But the only difference is in this example 7, the diagram isn't drawn for you. Okay, so you have to construct your own diagram using the information that they've given you here. Okay, but I think you should be able to do that, and all the maths that you use is exactly the same as I've gone through so far in today's session. Okay, so just to recap, what we did last was we used these 3 functions: sine, cos, and tan. Sine, cos, and tan, and these formulas that relate sine of your angle to this ratio of these 2 sides, cos of your angle to the ratio of these 2 sides. Sine is of these 2 sides, cos of theta is related to this ratio of these 2 sides, and tan of theta is equal to the ratio of these 2 sides. Okay. And you can use these formulas to find an unknown angle given 2 sides, or find an unknown side given 1 side and 1 angle. Okay. So that is really everything that you need to know from this study ready on right-angled triangles, the Pythagorean theorem, the sine, cos, and tangent functions. Yeah, that's all you really need to know. I would say, if you think you've understood it, then please try these last 2 examples that we didn't go through, but will be available online. Try these 2 examples. And if you don't think you've understood anything, I would kind of watch the session again. And then if you still don't feel like you understand stuff, then look at the extra study material that we have available on our website. Yeah, thank you for watching, and good luck in your studies next year.